Another important property of an electron beam that is in part determined by the source and the electron optics elements like apertures and lenses that we have in the system is coherence. Now, coherence is of course important for phase contrast imaging and for diffraction. And we have to remember here that when we talk about coherence in an electron beam system, we talk about coherence of the electron wave, the wave of a single electron with itself. And so electrons, unlike photons, cannot be all in the same quantum state, so they cannot be mutually coherent. There's two important things we have to distinguish, which is on the one side what we call temporal coherence, and on this other side spatial coherence. I will first talk about temporal coherence. Now, if we assume we have a sample in an electron microscope, so here I draw the sample. This is the sample plane. Now, if we have an electron coming in, that electron can be represented as a particle, but here we look at the wave properties. So that electron is represented as a plane wave. So we have a position here at which we know the phase, and then one full oscillation later, so a bit further down the path here, the phase is again the same. So we have this wave front traveling perpendicular to the direction of propagation, and at some point this plane wave hits the sample, and the sample will induce local phase variations in this wave, which then later in phase contrast imaging we project and convert to intensity contrast on our camera. Now, temporal coherence relates to the energy spread in the beam. So the fact that if we have multiple energies, multiple velocities in the wave, not all phase fronts travel at the same speed. So we have one specific energy propagating with this wave front, and then if they're all in phase at some point along the path, a lower velocity wave will go out of phase with the pink wave we depicted first, and will thus be out of phase on the sample. Another wave that is maybe slightly higher in energy will go with a slightly larger wavelength, and then also be out of phase with the original wave on the sample. Now, this temporal coherence is thus directly determined by the energy spread in the sample. The larger the energy spread, the lower the amount of temporal coherence, the narrower the energy spread delta E, the more temporal coherence we have in the beam. So also the longer the trajectory we can have before the wave starts to become decoherent. So for phase contrast imaging and diffraction, it's best to work with a low energy spread beam, for instance a beam generated by a cold field emission gun. Now, the other property is spatial coherence. And spatial coherence is a bit more complicated to understand, but spatial coherence relates to the lateral extent of the coherence of the beam. Now, to understand spatial coherence, we have to look at the plane in our electron beam column where the width of the electron wave is limited. And this can be an aperture, so let's draw an aperture here. But this aperture can also be the source or the virtual source from which the electron originates. It can also be the sample, where different parts of the sample transmit the beam towards the projection part of the lens. And we can look at any of these planes by understanding the Huygens principle. So the Huygens principle says that every point within this aperture, every point on the source, can be regarded as an individual source of new waves. So this point can be considered as the origin of a wave traveling, and this point can also be considered as a wave traveling further down the column. And then the total wave we have here is the sum of all these individual wave fronts. Now if we look at this situation here and we assume another plane, say again the sample that we have here, but like I said, we can also understand this by having this as the source or as the sample and the detector here. So then here we have, in this example, the sample. All these waves travel down to the sample. So here we have the straight path going down, and here as well. Now our electron optic system, our aperture, or what we get from the source or what we get from the sample down in the projection column, is characterized by a finite opening angle, the solid angle of our beam. So what we will in the end have here is a maximum angle here that we denote by alpha. And of course here it's the same, so this beam will also travel in this direction here with an opening angle alpha. And of course in the other direction it's exactly the same here, and it's the same going down here. So this means that if we look at a specific point on the sample here, we have different waves with different path length arriving. So the total contribution to the phase is determined by the one here, by the one here, and all intermediate ones. But these two are the most extreme, and this path length difference between the straight ray and the ray under angle alpha is determined by the triangle we have here, where we see that this is again the angle alpha, this is a 90-degree angle, and the path length difference is the distance we have here, which I will denote by d. Now also note that in this example we illuminate a specific part of the sample with the full wave cone, and this length here I will call x. And both these waves now have a different phase in this position. And so the path length difference now we can write d is x times the sine of alpha from simple goniometry. And we have seen that in electron microscopy the opening angles alpha are always very small, so that we can approximate the sine of alpha with the value of alpha in radians. So this equates to x times alpha. Now in order for the superposition of these two waves to still show a bit of coherence, we can see from the properties of a wave, so the phase will be like this. So as long as the difference in path length is less than half a lambda, we will have no negative interference parts in the total sum, and we will have still some degree of coherence, a positive contribution in the total phase here. So the path length difference should be less than half the wavelength. Now if we rewrite this, we see that there is a critical value, which we call the coherence length, which is equal to lambda over 2 times the opening angle. And so this means that if we know the energy of the electron beam, which determines our value for lambda, there is a specific, and we know the specific opening angle at which we're imaging, there is a distance on the sample or a distance in the virtual source from which we can extract a beam that can still lead to observing coherence effects in a phase image or in a diffraction image.